Good morning, everybody. My name is Akram. I'm a second-year PhD student at the Center for Quantum Software and Information. I'm working under the supervision of Dr. Christopher Ferry and Dr. Marco Tumamical. Today, I'm going to present one of the projects we are working on and show the main results we obtained. So, the problem we are talking about is quantum state estimation. So, in this problem, we have some quantum system like a microscopic system, an atom or an electron, and we want to characterize the system. So what a typical experimentalist will do is he will perform some measurements, and from these measurements he will obtain some data, some numbers, and from these numbers he's going to use some state estimation algorithm to find an estimate for the state. The state is a mathematical description that describes the quantum system, and if you know the state of the system, then we know everything about the system. So for the notation we're going to use, we are going to denote the true state of our quantum system by rho. Rho is a matrix that has some mathematical properties, and we have the measurement, which is described by some other matrix operator. We have the classical data, we call it phi hat t, and we have the estimate, which will be called rho hat. And typically we want our estimate to be as close as possible to the true state. The usual way we do this is through batch estimation. So we perform a bunch of measurements, and after we collect all these measurements, we use some estimation algorithm to find our estimate. The problem is that this requires a lot of time and space. So if we have this, if you have a system like an 8-qubit system, imagine you have 8 atoms, okay? So in order to perform the measurements, it will take in the lab a few hours, maybe 10 hours or so. But actually to do the processing, to do the computational processing, this might take a week or 2 weeks. So this takes a lot of time and space, and usually this process is repeated because the experimentalist tried to control his system. He has some controls, he wants to tune these controls, so he has to repeat this procedure over and over. So if every time he has to wait 2 weeks, then the experiment will take forever. So a better way to do this is through online estimation. So in this case, I don't have to wait for collecting all the measurements. As soon as I get a new point, I just use it to update my estimate and keep going on, and after having enough number of iterations, then we can obtain our estimate. Now the advantage of this architecture is at some point we can stop and say, okay, this estimate doesn't seem to be going in the right direction. So he can just stop, and instead of completing the whole experiment, he can tune whatever he wants to tune and then repeat again. So he doesn't have to wait for all the measurements to be done. He can just stop at any point and see how his estimate is going. So our problem is we want to design a quantum state estimation algorithm that's online. Most of the literature was talking about batch algorithms. The second thing is we want it as efficient as possible so that the computational time required is not that much. And also we wanted to have a convergence proof. We wanted to have some mathematical guarantee that this scheme will actually work. Also in the literature, most of the techniques doesn't have convergence proofs. They work heuristically, but we don't have an actual proof that they converge. So what we did is we ported an algorithm that was used in classical machine learning. It's called the matrix exponentiated gradient method. It was introduced in 2005 in the context of support vector machines and kernels. And what we did is we ported this algorithm from the classical machine learning domain to our quantum domain. So if you look into this update rule, you'll find that it relates the updated estimate to the old estimate and the new information we have. So we have here 2 terms. The first term encodes the past history we had, the previous estimate. And the second term, which is the gradient of the sum loss function, this term actually includes the new information, which is the new measurement we obtained. So it's like we are having a weighted average between the past history and the new information. What controls this trade-off is the learning rate. So if we choose a learning rate that is very high, then this term will have more weight, and then we are giving more weight towards the new information. If this learning rate is very small, then we give more weight towards the old history, and you can see if eta is equal to 0, then this term vanishes and the exponential and the log cancel out, and we get the old estimate answer. There is no update. Okay. We are dividing here by the trace because by the rules of the quantum mechanics, the estimate should have a trace 1. So we have to divide by the trace. And also there is another advantage that this result, this rule ensures that the eigenvalues of this matrix is always non-negative. And this is a requirement from quantum mechanics. Now the question is how we are going to choose the learning rate. This is a major part of our work. So the main results we have is the first case, if we are doing noiseless measurement, if we are doing an ideal measurement, the ideal case, then if we choose the learning rate to be any constant between 0 and half, then we can show a statement about the convergence of our algorithm. The second case is if we are doing noisy measurements, which is the practical case, and the noise here is statistical noise due to doing the experiment for taking the measurements for a finite number of times. Then the first way we can choose the learning rate is in this form. This ensures convergence, but unfortunately, there's here, this term is an expectation, and there's here the true state. But in our problem, we don't know the true state. So this can be a theoretical result, but practically you cannot use this form of the learning rate. So we look for another form, which is taking the learning rate to be decreasing with time, so it's proportional to 1 over t power beta. And again, we can show that by selecting beta to be in the correct range, we can again show a statement about the convergence of the algorithm. Another method we proposed is to use running average. So instead of updating using only the last or the new measurement outcome, we can take the average of this measurement outcome with all the previous history. So it's a kind like smoothing out the statistical noise that's happening over time. So after enough number of iterations, we'll actually be very similar to the noiseless case, which we already had the proof of convergence. For the numerical results, we did a number of simulations on the UTS cluster facility, and the first result here is the effect of choosing the learning rate. We are plotting here the infidelity. The infidelity is a number that's between 0 and 1. 0 means that we are at the true estimate, so we found the true state, and 1 means that we are so far. So ideally, we want this infidelity to be as small as possible. And we have here the number of iterations. So you can see here that using this running average method gives the best convergence result. So this is the method we choose for comparison. We compared with two other methods that are widely used by experimentalists, which are the matrix, which are the maximum likelihood, and the least squares. And you can see here that in terms of accuracy, all of the algorithms have almost the same performance. But actually, these algorithms are batched. So we have the advantage that our algorithm is online. And also we have a convergence proof, which is also something better than the other two methods. In terms of complexity, calculating the complexity per one iteration, the results we found is that for our proposed algorithm, it scales as d power 3, and d is the dimension of the matrix. While for the other two methods, it scales as d power 4. So this is more efficient. And we also did measure the actual simulation time. And you can see here from this graph, for example, that the time it takes to do the procedure for 6 qubits by maximum likelihood is almost the same time it takes to do 12 qubits with our proposed algorithm. So our algorithm is much more efficient. So to conclude, we were solving the problem of quantum state estimation, where we perform some measurements and we want to find an estimate for the quantum state of the system we have. And what we did is we ported a classical machine learning algorithm, which is the matrix exponential gradient. We proved convergence for noiseless and noisy measurements, and we numerically compared our algorithm with the methods used by experimentalists, and we showed that it's as accurate as the other methods, but at the same time it's much more efficient. And finally, I'd like everyone to have a look at our paper. We have just been published a few weeks ago. So, if you have some time, you can check it. Okay, thank you.
Any questions?
At some point, do you want to invest this at the IBM public computers?
We didn't test this experimentally yet, but this was one of our future work to actually test these things on a real set.
Yeah.
Could you go back to the one of the first slides where you had the equation for the update rule for the estimate? The intuition of the equation, I guess, is fairly clear, but is there reason to believe that that's an optimal rule to use? Is that,
Yeah,
is
so
that that's the
actually-
best you can possibly do?
Yeah, so actually, this is the final result, but actually you can, this comes from solving an optimization problem.
Mm-hmm.
So what we want to optimize is, we want to minimize the distance between the new estimate and the old estimate, because we don't want to forget all the history we learned, and at the same time we want to minimize the sum loss function.
Mm-hmm.
So forming a cost function as an average of these two objectives, and solving the optimization problem by minimizing with respect to the estimate, we get to this rule. So actually we can derive this rule.
Great. Okay.
Can you just go to slide 7, please? Why do they cross? Yeah.
So this corresponds to taking beta equals 0.5. So we are choosing the learning rate to be 1 over square root of t. So whatever, this graph shows that whatever the index you choose here, the running average will be better than any of them. Because we have a finite range of these indices so that we can prove convergence.
So in the capacity comparison,
Yeah.
you mentioned that you have D cube capacity
Yeah, this is per one iteration, per one update.
for one update.
For one update.
Because you have the exponential function?
Hmm?
Because there's exponential function?
Yeah, because of the exponential function. Yeah. So the way we do the exponential is by eigendecomposition, so this has complexity d power 3. The other methods, the actual update rule will require matrix multiplication, and this will be d power 4. Any more questions?
So I have a question. So at the start, you suggested that the time using these batch processing is potentially weeks. Is that right? I mean,
Yes.
so this is for a practical quantum computer system.
Yeah,
So
so
you're trying to make measurements of quantum it takes weeks to really think that.
yeah, so the actual experimental thing, applying lasers and things like that, takes maybe a few hours, but the actual processing to find the inverse of this matrix takes weeks. And this is the actual example is for an 8-qubit system. It takes I think about one or 2 weeks, and 8 qubit is very small. So if we have 1,000 qubits, this is impossible.
And so in your algorithms, the speed up is what? 1-2 orders of magnitude from this comparable.
So the main thing is here is that here we don't have to perform all the measurements and then process them at once, which takes this whole time. We can just keep doing the measurement and doing the updates. So at some point we can just stop. We don't need to complete that. If we find that the estimate is not converging to what we expect, then we can just stop the procedure at some point. But here we cannot. We have to do all the measurements and wait for 2 weeks to find the result and discover, oh, this is not what we expected.
The way you've got it in the second line with that pipeline, it's discretized. Is there a logical way to generalize this to some sort of continuously evolving system with weak measurement or something like that?
Well, that might be an idea we could explore, but yeah, we didn't look into it.
Great.
Into this one.
So you choose the learning rate in some functions.
Yeah.
So how do you know what is a good learning rate? Is there like a way to decide on what this learning rate should be, or is it how do you decide
Yeah.
what's a good learning rate?
So when we do that theoretical analysis, we can show a range of the learning rate which we can choose from. So for example, in the noiseless case, you can choose any constant between 0 and 1. Okay. Now, what exactly the number we are going to choose? This is the numerical part. So when we do the numerical experiment, we just try with different learning rates, and usually, if we increase the learning rate, then we'll converge faster in general. So in this range, if we choose eta equals to half, in this case, then this will give the fastest conversions.
The choice in the learning rate therefore depends on the working software. Is that it?
No, the conversions of the algorithm depends on choosing the learning rate. But the way so in order to find this range, when we do the theoretical analysis, we selected such that we ensure that we can show statements like that.
There's another question that's